Have you ever looked at those massive multi-screen displays in command centers or retail spaces and wondered how the image perfectly spans across multiple monitors, like without looking like a glitchy, unaligned mess? Welcome to your custom deep dive. Today we are tearing into a highly technical product page for the Avenview DVI-ProWall-4X Videowall processor. Our mission is to decode the hidden tech drive these commercial digital canvases. Okay, let's unpack this.
Yeah, it's really easy to look at a 2x2 video grade and just assume it's, a single monitor chopped into quadrants.
Fine.
But technologically speaking, maintaining subframe latency while pushing one high-resolution image across multiple distinct outputs is, it's actually computationally intense.
Right, like the core of what this Avenview processor does is take a single DVI or HDMI input and distribute it across 4 displays in real time. And it supports standard grids or even custom mosaics. But taking a single image and expanding it that much, that is where the math gets really complicated.
Exactly, because if you just stretch an image, it looks terrible.
Yeah, I'm imagining a master pizza chef taking one massive ball of dough, which is our source video, and stretching it out to the size of 4 pizzas. But if you just stretch dough, the toppings thin out and rip apart, right?
Okay.
So to prevent the digital image from looking like a blurry, stretched out mess, this processor must be doing something to actively fill in the gaps.
What's fascinating here is exactly how the real-time processing chips handle that scale. It uses a highly specialized embedded scaler. So going back to your pizza analogy, the scaler acts like a chef who magically generates new toppings in real time as the dough expands.
Oh, wow. So it literally creates new data on the fly.
It interpolates the data, yeah. It generates entirely new pixels to match the native resolution of the connected monitors, up to WXGA or Full HD 1080p. Without that constant real-time pixel interpolation, the visual fidelity would be just entirely compromised.
But scaling the pixels is really only half the battle, because if you perfectly scale an image across 4 screens, you immediately hit a physical roadblock, which is, well, the plastic borders of the TVs themselves. And looking at the specs, this processor carries a price tag of $3,995 and weighs about 3.2 pounds. Here's where it gets really interesting. Is this overkill? If I'm spending $4,000, I assume I'm getting significantly more than just a cheap video splitter from a big box store.
If we connect this to the bigger picture, the difference between a standard distribution amplifier and a true video wall processor becomes really clear. A basic cheap splitter just clones the exact same image 4 times.
Right, which isn't helpful for a seamless wall at all.
Exactly. The Avenview enables independent display area control for each output, meaning you can dictate exactly what quadrant goes where and even manage input rotation. But the critical feature for dealing with those physical roadblocks you mentioned is the on-screen display, or OSD, configuration for edge correction.
So instead of the image awkwardly jumping across the gap from one screen to the next, it calculates the exact width of the bezels. Like it virtually renders the missing pixels behind the physical borders.
Yes, it tricks our eyes into seeing a continuous window. It virtually masks that portion of the image so the geometry of the picture remains perfectly intact.
Wait, so how do you even manage that level of granular pixel-perfect calibration? Because that sounds impossible to do manually.
Well, the processor bundles its own control software accessible via USB and Ethernet. This allows users to precisely resize, position, and zoom the output video to choreograph complex surveillance systems or educational displays. And you can actually save those custom layouts directly to the hardware.
So what does this all mean for you? Well, the next time you see a flawlessly aligned video wall, you will know the immense computational heavy lifting happening behind the scenes. And impressively, this specific processor manages millions of interpolated pixels across 4 screens without dropping a frame, while only drawing 7.6 watts.
Which is less than a standard LED light bulb, actually.
Yeah, it's crazy. It really puts the hardware into perspective. But it leaves me with one final thought for you to ponder. If a 4-display processor requires this level of sophisticated real-time scaling and a near $4,000 investment just to seamlessly manage a 2x2 grid, what kind of unimaginable computational horsepower is required to run the massive, seamless 360-degree LED arenas being built today? Think about that the next time you see a giant digital campus.